Hello, this is Lab 5, Faraday's Law by Ryan McKee. The purpose of this lab was to use Faraday's Law and the Biot-Savart Law to model a magnet falling through an aluminum foil tube. First, I measured the time it took to drop a magnet through an aluminum tube in real life. Then, I used GlowScript to create a model of the system using provided starter code. Finally, I compared the observed time from the model's projected time. There are many fundamental models and principles used in this lab. The physical principles include the force of gravity and magnetic force, which describe types of attraction forces between two objects. These forces combine to create the movement of the magnet in this lab. A magnetic force is exerted on the magnet due to the current induced in the aluminum foil. Faraday's law was used to model the magnetic flux. The equation can be seen on the slide. Newton's laws were also used to find the gravitational force and related the force on the magnet to the force on the tube. In this lab, I found that it took around 0.37 seconds for the magnet to fall through the hole. My coding model found that the magnet should take around 0.225 seconds to fall. The shown photo is a screenshot of the text output of my code. In the experiment section of this lab, I dropped a magnet through a roll of aluminum foil and took a video of the process. Then I measured how long it took for the magnet to travel through the tube. I repeated this experiment 5 more times and found that the average time it took for the magnet to fall was 0.37 seconds. In this lab, the system was the magnet and the aluminum tube, while the surroundings was my hand and everything else. The initial condition was the magnet suspended motionless above the tube. Next was the coding section of the lab. In this section, I used my data and the starter code to create a model for the magnet falling through the tube. First, I found the magnetic flux and induced current in the loop. Then I found the total force by combining the force on the magnet due to gravity and the magnetic force from the rings on the magnet. Finally, I ran the simulation to find the theoretical time it takes for the magnet to fall through the tube. The model was fairly similar to real life. It showed that the magnet should be falling in 0.225 seconds, slightly faster than the real-world example showed. This discrepancy could be due to friction slowing the magnet's fall in real life. Both the computer model and the real world were similar in that they both showed the same system. I assumed that only the force of gravity and the magnetic force affected the magnet. This is reasonable because I didn't have the ability to solve for any other forces. I also assumed that no other magnetic fields acted on the system. This made sense because I was far from the walls or the floor, and the magnetic field from the magnet was much stronger than any other in the region. Some potential sources of error in this lab was friction with the side of the tube. Bumping with the walls of the container could have slowed down the magnet in the real world. The frame rate of the video could have introduced error because it made it impossible to capture the exact time the magnet entered and exited the tube. Outside magnetic fields could also have affected the flux in the aluminum foil, causing error. What if the resistivity of the conductor was reduced to essentially zero? If the resistivity of the foil was essentially zero, then the induced current in the foil would be huge. This would cause a strong magnetic reaction to any magnetic flux. This means that the magnet's fall would be slowed significantly, if not stopped. What if holes were cut into the foil? If holes or slots were cut in the tube, it would break some of the current rings. This means the foil would generate less induced current and a weaker magnetic reaction to a change in flux. Thank you.